Okay. So the plan for today's session is to go over like midterm 2 questions, like any questions you can remember. I think I know the synthesis one, there's like the meta bromines. There's some like predictive products ones with the conjugated diene, ranking the molecules in exothermic, like how much energy they have as well. What else? Like the weird Diels order problem with the electrocyclic, like you gotta open up the diene first and then do the Diels order as well. And then this week we're gonna finish hopefully chapter 17 next week, chapter 18, and then the last week, week 10, just final review, like from old material to new material. Right. So let's see. I remember one of the problems was something like this. And then it was like, was it a dienophile? Trans, yeah, I see. Dang, this is a tricky one then, because like there's gonna be 4 different products here, right? And this is under heat. So first, we see a dienophile, but this is not our diene here. This is a ring where we could see a ring opening with heat. So first we just ignore this dienophile, and then we draw the arrows of the ring opening, which is gonna be like that, right? Where we see 2 arrows, an even pair of electrons and heat that is conrotatory, right? So when I ring open it, let's say this goes counterclockwise, this has to go counterclockwise as well. What are gonna face away from each other, right? So when I open up the ring, I get this diene where the methyl groups are facing away from each other like that, right? And then we have the dienophile here. Now we can do the regular Diels order reaction where we see that these methyl groups here are out groups, right? And we have nitriles here, which are the EWGs. So when we do the Diels order reaction, we could get this product here where the out groups are cis to, let's say, this top nitrile is a EWG. It has to be dash like that, right? And this bottom nitrile has to be trans to that nitrile right there. So this is the first set of possible molecules. I think, I'm not sure though, but I think this is another set that he might have looked for, where the EWG is the bottom nitrile, and then the trans group is the top nitrile. And the enantiomer version of that as well, right? Because these 2 are different molecules here. If you made the top nitrile your EWG, your out groups would have to be cis to that EWG. This nitrile is trans to that EWG, so that has to be trans to that EWG as well. But if you said this nitrile was your EWG, then that nitrile has to be cis to the out group, making the other nitrile trans to that group right there. And this is different than that group right there. So I don't know if you wanted 4 products or if he just accepts like that right there. Okay. Another question was something like, let's say the synthesis problem, start with the empty benzene ring, and then you end up with the meta bromines here. When I saw this, I was like kind of confused because I was like, they're meta to each other, but this is orthoparadirecting. And then this is what like most people did. They did sulfonation, which will add a sulfonate group to that carbon here, right? And we know that's a meta director. And then you could say excess Br2 FeBr3, which will add bromines meta to that sulfonate group. And then we could get rid of that sulfonate group by using acid, H3O plus, and heat, or H2SO4 and heat, right? But that's kind of weird because let's say you add one of the bromines first, right? Meta to this EWG here. Now we have a competition between this sulfonate group and that Br there. This is a strong EWG. This is a weak EWG. Weak EWGs are not as deactivating as that strong EWG. So I would say this takes priority over the SO3H. So the second Br would be ortho or para to that Br, which the second Br would be here or here. But that's how I got confused. Right. So I think this is still acceptable though. Like when you put excess Br, the Br should be better to that, but I'm not too sure of that. Okay. Is this what you guys got as well for the synthesis? Nice, nice. Okay. Okay. So let's see what else. Okay, let's say something like this. Okay. Okay. Let's say this is A, B, C, D, E. And we're gonna rank these in order of increasing energy. So let's see. Which one of these is going to be the most exothermic? Which one is the one that has the most amount of energy? Right. So when we think about this problem here, energy, what is the relationship between energy and stability? Are they directly proportional or inversely proportional? Inverse, right? So if we're looking for the one with the most energy, we have to look for the one that is the least stable. And the one that is the least stable is the one, oh wait, let me make this here. That is not conjugated at all. These three double bonds here are not conjugated, right? So this is the one that is going to be the most exothermic, right? Because it is the one that is the least stable. Which one of these is the most stable here? A, right? Because that is conjugated with three double bonds, but this is also conjugated with three double bonds. But this is aromatic, this is non-aromatic. Aromatic structures are more stable than non-aromatic structures. So since it is more stable, it has the least energy, making that the least exothermic, right? And then we could say E is the second most stable because it has conjugated diamines here. But this is also conjugated diamine here, right? But this one will have yeah, since this is non-conjugated, this one will have more energy than this one because that's non-conjugated. See, B, and then E, and then C, and then A. Right. So the order of this ranking system goes something like this, where this has the most energy and the right side has the most stability. Right. Yeah. These two here are not conjugated, and then the three on the right is conjugated. That. The reason why E has more energy than C is because they have more double bonds, and it requires like more energy to break those double bonds. Okay, so let's see. Another type of question was predict the reagent on the arrow, which was something like this. Let's say we have that. Here. What did you guys put for this here on the arrow as a reagent? Or I'm not sure if this was on the exam, but someone just showed me this, and I'm not sure if this was on the exam or not. Yeah. Right. Where in the product we have a X halogen, which is the Br, and a double bond. This double bond is in its most stable position. And what kind of product is that from a conjugate diene? Kinetic or thermal? Thermodynamic, right? So since we just have a Br there, the reagent is going to be HBr and like at least 40 degrees Celsius. Or you could say heat. I think that might be acceptable. I'm not sure. Right. But we want the thermodynamic product because we have the most stable double bond here. Okay. Let's see. What was the other one? How many diagnostic peaks does this terminal alkyne have here? So this terminal alkyne has a C, triple bond C, which shows a sharp peak at around 2100 to 2300. It also has an sp carbon hydrogen peak, which shows up as a sharp peak at around 3300. Right? Since this is asymmetrical, there's no negligible peak. So we have two diagnostics peaks, two peaks that tells us that this is a terminal alkyne. Right. Yeah. Let's see, what was the other question? Let's see, decompose order, benzene. Oh, right, the mechanism, the Friedel-Crafts and when you have toluene. How many of you guys remembered toluene? Like on the test, you guys okay? I said a lot of people like they got confused when they saw the word toluene. They was like, what the heck is a toluene? Right. Which is a benzene with a methyl group on it. Right. And he wanted you to draw the mono substitute, like mono addition from this reagent and AlCl3. Right. We know this R group is an EDG. So it is orthopara-directing, where the major product is going to be at the para position here. Right. So did you guys get that as the product? Nice, nice. So I'm just gonna speed run this mechanism and then see if you guys get that. Say Cl, AlCl3, check that. The Cl here becomes a good leaving group. Yeah, right. Where this is our good leaving group here. That good leaving group is just gonna leave by itself. Think of it as an SN1 reaction now, where we're gonna form a carbocation there, right? And the good leaving group that left becomes this right here, where the aluminum with 4 bonds still has a negative charge. Now our benzene ring with the methyl toluene is gonna use this para carbon to attack that carbocation right there on that R group, right? At this point here, we always have to look out for rearrangement, but there's no hydride or methyl shift because it's already in its most stable position. So we didn't have to worry about that in this case, right? So then when that happens, we are going to break the aromaticity because we're going to use this bond here to make a bond between this carbon and that carbon right there, which is going to give us this structure where we're going to now reform the aromaticity by bringing in this base. And the Cl here is going to attack that hydrogen and form a double bond there, elimination, which is going to give us our final product here. And the side products would be like HCl, AlCl3, right? HCl comes from this elimination step. The Cl grabs the H to become HCl. The metal catalyst gets reformed there as well, right? Okay, let's see what else. Yeah.
I think there was the one where it's like benzene to di or meta digrupple.
Right. Yeah. Did you get this this route for synthesis here? Like it's kind of weird because once you add the bromine once to the sulfonated group here, this would take priority, where the next bromine would be like here or here. That's why I got confused, but I think if you put X as BR, he would accept this as well. Yeah.
That's what I thought too when I was doing that. I was like, I feel like that would like take over. So I was stuck on that one for like 10 minutes.
10 minutes, yeah.
But I was like, I'll just do
You
it.
just stick with this one, right? Yeah.
Like, would it be okay if I actually did I did BR2, FEBR3, but as two separate steps? Would I get dot points from that?
No, it's the same thing.
Okay.
Yeah, BR2 and then yeah, and then from there you did BR2 again to get to that point.
Yeah.
Yeah, I think that's fine as well. I remember someone telling me that Pascal says strong EWG takes priority. And they asked if that's right, but I was like, no, weak EWG takes priority. But going with his case, if he says that, then it would work. Yeah.
Is there any other way to solve this in that case?
I don't know. I was thinking about this for so long. I was like, what can I do? I try to make like a group there. Yeah, I don't know. Yeah. Let's see what else.
That
Yeah.
question about, I just wanted to like check in on this, the one where it was asking us to rank from like most to least exothermic.
Oh, right. Most at least exothermic.
Oh.
Yeah. And so D is going to be the most exothermic because it has the most energy since it is the least stable, not conjugated at all, and the most amount of double bonds to break. A is the most stable aromatic ring, so it has the least energy, the least exothermic. Everything else is in between.
Right, but
Yeah. But that's like, so a lot of people, they thought about stability, so they reversed the order. They said this was the highest one because they were thinking about stability, but stability and energy are inversely related. The more stable the molecule is, the less energy it has, the less exothermic it is. Yeah. Let's see. Someone sent me this as their NMR, but I'm not sure if this is right. I think the DOU was like 6. Yeah. Let's see. Someone got this, but I'm not sure. Terminal alkyne. Right. Because I think on the IR, there was a sharp peak at 3300, and then a sharp peak at around 2100. Yeah.
I think I did that, but like
Uh-huh.
I closed that ring and then the CL was on a was attached to another carbon. Like if you the if you the atom upon which the chlorine is attached to, if you draw a carbon instead of chlorine, and then make that like almost a pentane ring, but the oxygen is replacing carbon, and then one of those carbons has a chlorine on it, I think. And then at one of those points, there's an oxygen.
And then chlorine right here.
Yeah, that's what I got.
See. I think this has an extra carbon here because this one, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay. Let's see. Yeah. Okay.
I'm just like curious, how did you learn these CDs?
Oh, I know people just tell me yeah. Some of the questions, yeah. I'm trying to remember what else they told me. Yeah. Let's see. This was the mechanism. This was an interesting problem. Like I've never seen a Diels order been asked this way. Like you have to open up the ring to become to make a diene and then do the Diels order that way. Let's see what else. The terminal alkyne has 2 diagnostic peaks. Let's see, do you guys remember any problems? Predictive product. I think it was. Not sure. Oh, yeah, turbidor.
He said that it was supposed to be a reaction, but it's
Oh. There was something like this, I think, with the aldehyde,
Yeah,
and then
it was asking for real press as like Friedel-Crafts reaction in general, but I put no reaction because
The activated ring. Yeah, that's right. That's right. Nice. Uh-huh. Okay. Let's see. Aldehydes and ketones. Aldehydes and ketones, yes. Trying to find that. No, no, the naming one. Oh, and then there's also something like this, right? Like, what's the bond angle? Oh yeah, it's not 90, it's not 90. It's supposed to be 180, right? Of the structure here. Oh, that wasn't an option?
Yeah, it was 0.
It was 0? Oh, oh, okay.
Oh,
It was
Yeah,
0.
same thing.
But they're SP2, so they're playing.
I know. Well, this is an allene, right? Yeah.
I think the question was asking, like, based off of the two cyclopropane, like groups there, in relation to the planes that each of them give off, what are those angles? And I put 0 because those are on the same plane.
Yeah, same plane. Yeah, yeah. Right. Yeah.
Yeah, I think it's tricky. Say the 2 planes.
Thing, yeah.
There was another question, I think I remember now this one, where it was asking what was the aromaticity of
This thing, right?
annually? Oh, yeah.
Yeah.
I think
I think it was non-aromatic because of this like steric hindrance. Oh wait, but in lecture he said this is aromatic. Oh, anti? Well, if they are like conjugated to each other, right, and this alkyne can do resonance, this would be 1, 2, 3, 4, 5 pairs of electrons that are resonating. 5 pairs is an odd pair aromatic, right? It would be anti if this was an even pair of electrons that are resonating, because only one bond of the triple bond is resonating, not 2 bonds. Right? Yeah.
I think I did answer non-aromatic on the test, but how would we know that those two hydrogens would be stereochemically different?
Because of the steric hindrance here, like the points are so close to each other, they want to avoid each other, right? It can't be flat planar because that's too close. But in the lecture, he says this like it's aromatic with the original thing here, right? But the book says this is non-aromatic. So I'm sticking with non-aromatic, right? Yeah. Because of steric hindrance here, like the points are so close to each other.
And then you will argue it because he's like,
Yeah. I would argue it if he doesn't give you the points back to that. Yeah. And then 2 diagnostic peaks for a terminal alkyne. Because the sharp peak at 2100 to 2300, and then the sharp peak at 3300. Yeah, this is not diagnostic. The 3000 sp3ch, that's not diagnostic. It doesn't tell you what functional group you have. Right. Something about the NMR was like that. I don't know. Right. C9 A7 COO IR. And which one of these are wrong? I think this was wrong because like the common name of that is toluene.
There was one option. It was like O, chloro, bromo, or dichloro. It was like 2 halogens. And then, and then I said that one was wrong. This is one, 2.
Oh.
I don't know.
oh yeah, it
Yeah.
was they said it was like ortho.
They said O.
Oh yeah, that's wrong. That's wrong. Because O, M, and P, they need 2, only 2. 1, 3 or 4 or 5, then you can't do O, M, or P. Yeah.
I remember he did an example example in lecture.
Uh-huh.
It was like a styrene or something like that. where it
Styrene.
had two substituents, so it was technically like a styrene, or like it was like a benzene with an ethyl, an ethylene, I think.
Uh-huh.
So like an, or like a, yeah, ethyl, yeah, an ethyl group,
Uh-huh.
but with, oh my god, I can't remember the nomenclature right now. But it was like ethyl and then, with an alkene at the first carbon, like hanging off of the benzene. But it was like the styrene, I think that's what it's called.
Yeah, styrene. This
Yeah.
the styrene. Uh-huh.
That, it had like the two other substituents. But it was just, it was like, it was like ortho with the substituents and then the
Mm.
name styrene.
Oh, right, yeah, because this would like take priority if like this was another R group there. If it was an alcohol, then this phenol would take priority.
No, but it was two substituents.
Oh, I see. Yeah.
You're using that as a foundation. So if we treat the whole styrene group as a functional group.
Yeah.
Would we be able to like argue orthometapara, although it's not exactly just a benzene? Like, let's just say,
Yeah.
let's just say take two chlorine groups
Uh-huh.
and place them somewhere on the ring. Could we just call that, okay, yeah, and that, would we call that like meta dichloro,
No. You can't do that.
yeah, okay, so
Yeah.
then that means that the orthophenol thing on the actual test was wrong.
Yeah. Uh-huh. Okay. And then one of the questions was like, if you have a benzene ring and then you have Cl2 and then the metal catalyst was like FeBr3, will you get a product? And if you do, will it be mostly chlorinated or brominated? Right. I think the answer is like mostly chlorinated. It will still work, but mostly chlorinated because it's the X2 here. Yeah. What else? Oh, no, this is just extra practice. Okay. Yeah, let's see. Yeah, there you go. Nice. Okay. Okay. Any other thing on the midterm before moving on to the new chapter? Okay, so let's start chapter 17, which is the aldehyde and ketone chapter. Okay. So an aldehyde is an R group, carbonyl, and a hydrogen right there. Ketone, we're gonna have two R groups around the carbonyl here, right? So aldehyde is like the hydrogen hiding. Here, aldehyde, hydrogen hiding. Ketone, you can think of it as like this is like a key kind of, and then the carbonyl is alone. Ketone, carbonyl alone. Okay. So now, which one of these do you guys think is a better electrophile? Right? Which one of the carbonyl carbons here has a bigger partial positive charge? And why do you guys say that? Right. Aldehyde has an H, right? And there are R groups. And are R groups EDGs or EWGs? EDGs, right? So the R groups here are going to donate electrons into that carbonyl carbon right there, right? So the aldehyde here only has one R group, only one EDG. The ketone has two EDGs on it. So this ketone carbonyl carbon here will have a smaller partial positive charge. The aldehyde will have a bigger partial positive charge because the aldehyde only has one EDG, whereas the ketone has two EDGs here, right? And if this carbonyl carbon is gaining more electrons, it's gaining more negative charge, which makes it a smaller positive charge there. Right? This only has one EDG, so not as much electrons being gained there.
Okay, so then if you're saying that, oh wait, yeah.
Right. So this would be a better electrophile than the ketone here.
Okay.
Right. Okay.
Wait, I thought, I thought, electrophiles are EWGs and then that would make, oh, no, just kidding.
Uh-huh.
Give myself a-
All right. Like this right here, like if we'll attach to a benzene ring, then this would be considered EWG, right? But we're just looking at, like we're treating this as a system now, and then this is the very first atom that's attached to the system, which is the R group. And R group is an EDG there, right? An even better electrophile is formaldehyde. A formaldehyde is a carbonyl with no R groups at all, just two hydrogens, no EDGs at all, right? So this is a an even better electrophile, bigger partial positive charge there, right? And then now let's learn how to prepare aldehydes and ketones. Preparation of aldehydes and ketones. Now, most of these are you guys already know, you guys already learned about. The first one is going to be, let's say, from alcohol. This is back in 118A. Let's say we have a primary alcohol, something like this. Right. What reaction do you guys know can make this primary alcohol into an aldehyde? Yeah, PCC. That oxidizing agent can turn that primary alcohol into an aldehyde here. What if we use Jones, a stronger oxidizing agent? What would this primary alcohol turn into? It's not going to be an aldehyde or a ketone, but it's going to be a different functional group. Yep, carboxylic acid. Nice. Okay. If you have a secondary alcohol, right, it doesn't matter what you use. You could use PCC or Jones, any oxidizing agent. You're always going to get a ketone. Right. For tertiary alcohols, if we try using PCC or Jones, will a reaction even happen or no? Yeah, no reaction. NR. Right, because there's no hydrogen on that carbon there holding the alcohol. Nice. Okay. So there's a new oxidizing agent, which is even weaker than PCC. Let's say we have this structure here. And then we have the reducing agent, oxidizing agent, MnO2, manganese oxide. Have you guys seen this oxidizing agent before? Right. So this oxidizing agent here can only oxidize allylic or benzylic alcohols. Right. So we know that this position here is allylic. So that alcohol here is going to get oxidized. Will this alcohol also get oxidized? Is this position allylic? No, since it's not allylic, this alcohol would not get oxidized, right? We only oxidize the allylic or benzylic alcohols. So that alcohol will not react. It will stay the same right there. It stays untouched. But this allylic alcohol here gets converted to a ketone there. Yeah. In this example, it is meta, but we could have different examples like this. Like let's say we have a benzene ring like this, and then we have a cyclo pentane like that, and we have an alcohol here and an alcohol here, and we put that through MnO2. Which alcohol will get oxidized? Here. Yeah, the benzylic one, where this alcohol here is ortho to this ketone. So it doesn't have to be meta. I'm just trying to show that the allylic or benzylic alcohol gets oxidized. Any other alcohol that is not benzylic or not allylic stays as an alcohol. It doesn't get oxidized. Yeah.
Let's say both the alcohols were lower.
Yeah.
Do you need to say two equivalent to excess MnO2?
No, you could assume excess, right? It's like H2PDC where it will reduce an alkyne all the way down to an alkane. Or ozonolysis where if you have multiple double bonds, you cut all the double bonds in half. Yeah. Or like if you have multiple alcohols and you put that through Jones, it will oxidize all those alcohols as well. Yeah. Okay. So another method to form aldehydes or ketones is ozonolysis, midterm one material, alkene. Right. Let's say we have something like this. And a mixture of the last midterm too, with the benzene. Like that. And then this reagent here, O3. Second step, let's say, okay. What will happen here? Do we cut all the double bonds in the structure? Yeah, we don't touch the benzene ring at all because the alkenes in the benzene ring are aromatic, conjugated, and stable, unreactive. We can cut this double bond though, that is not in the benzene ring, right? So we're gonna cut this double bond in half and put oxygens in the middle like that. Don't touch that benzene stable ring. Right. Once we cut it in half, we get these two products here. Ketone. And this is an aldehyde right here. You can draw out the hydrogen. I recommend drawing it out because we usually draw aldehydes with its hydrogen like that. Okay. Okay. So let's do one more tricky example with ozonolysis. Say, yeah. Okay. Try predicting the products of this structure if we have ozonolysis conditions. Uh, can you say this is aromatic if this is not benzene?
Yeah.
Oh, right. So to be considered aromatic, you have to fulfill three conditions.
Oh,
Right. It is cyclic.
but like,
Yeah. And fully conjugated aspect as well. sp3, sp3, sp3.
sorry, I guess what I meant to ask is like, can you cleave a ring if it's not like aromatic?
Yes, yes, yes. You can cleave a ring if it's not aromatic. And that will break open the ring. And it will stay as one molecule if it's in the ring, because like when you're breaking open the ring, it just opens up into a linear chain, right? But if your alkene is already in a linear chain at the beginning and you cut that in half, you get two separate molecules, right? Because you're cutting a linear chain into two smaller fragments. But if you're breaking up a ring, that stays as one molecule, but now it's just open and linear. Yeah. So, cut. Okay. It's weird. Form aldehyde. Aldehyde. Whoa. Right. If you write your answer as this, you could just leave it like that. That's the exact same thing. Or if you have like time at the end, you could number it and then redraw it where it's like straightened out. Okay.
It's like. Good point,
Uh-huh.
like, you see the bond, like, on the cyclic, where you have the range, the bond on the right side?
Right, this bond
Yeah,
there.
that one, like,
Yeah.
how does it reach? How does it get longer? You have like, you know what I mean?
Oh yeah. So this is weird. It's not supposed to be like in this form. It usually doesn't exist like this. It will straighten out and flatten out to like the zigzag form that we're used to seeing.
Okay.
This is just a way to predicting the products
That's
here.
the way I was going, so when you draw it, the oxygens don't have to be right next to each other.
Yeah. They don't have to be right
Probably
next.
can help regular with substitutions.
Yeah. Right. I just do it like this because we clearly see where the cup was here. Right. Which when you redraw it, you could do something like this. You could number it like, let's say 1, 2, 3, 4, 5, 6, 7, 8. Longest chain 8, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. At carbon 2, ketone. At carbon 5, ketone. Carbon 6, coming out of that carbon, aldehyde. Carbon 7, ketone. Right. So now that this looks much more nice there. Much more nice. Yeah. Okay. Now we could also create aldehydes or ketones by mercuric ion catalyzed hydration of alkynes. Okay. So I'll give you 3 different kinds of alkynes. They're going to go through the same conditions. Let's say I have this terminal alkyne, this symmetrical internal alkyne, and this asymmetrical internal alkyne. Put them through HgSO4, H2SO4, water. Okay. Is this a Markovnikov reaction or an anti-Markovnikov reaction? Hydration of alkyne. Markovnikov, right? Because we have mercury here, and when you see mercury, always think of Markovnikov. Like in alkenes, it was oxymercuration, demercuration. In this case, this is hydration of alkyne. For the terminal alkyne, the Markovnikov position, the more substituted position is that carbon right there, right? Where it's going to go through this intermediate right here. Right. We're going to add the alcohol at the more sub position where the alkyne becomes an alkene. But we don't stop there. What else do we have to do at this point? Right. What is this functional group here? Enol, right? Tautomerize into the carbonyl. Nice. Right. So we formed a ketone here, specifically a methyl ketone from a terminal alkyne. How many different products we would get for the symmetrical internal alkyne, and how many different products we would get for the asymmetrical internal alkyne? One for the symmetrical, because it doesn't matter which carbon you put your carbonyl at. It's symmetrical, so it's gonna be the exact same thing. Let's number it just to make sure. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right. For asymmetrical, you're gonna get 2 different products. Right. Where these are different from each other. Different connectivity. These are constitutional isomers to each other. Because if you put your carbonyl here, you get this. If you put your carbonyl on this carbon, you get this product. Where this carbonyl is closer to the isopropyl group, and this carbonyl is further away from the isopropyl group. Okay. So that's why they're different. Yeah. Next. Yeah. Okay, last one. Hydroboration, oxidation of terminal alkyne. Okay. Let's say we have this terminal alkyne here, and we put that through R2BH-THF, second step, H2O2, NaOH, water. Is this a Markovnikov reaction or an anti-Markovnikov reaction? Anti, right? So we're going to put the alcohol at the less subposition of the alkyne, which is this carbon here. When we do that, we get this enol, which will tautomerize into the carbonyl here, where we have a hydrogen right there. And I'm going to draw that hydrogen up explicitly to show that this is an aldehyde. You always get an aldehyde from hydroboration oxidation of a terminal alkyne. That's always your product, an aldehyde. Okay. I'm gonna have you guys think about this synthesis problem for like 2 to 3 minutes and see what steps you guys would do here. Let's say that. And we try to create, let's see, 1, 2, 3, 4, 5, 6. That. Okay. When you guys think about a first step, let me know what step you guys think we could do here. Yeah.
Or you could do like a green.
Right. So that's good. I wanted you to answer that, but there's gonna be a problem here when we do Grignard. Like, and since we're adding new carbon-carbon bonds, right? The very first thing we think about is Grignard, right? And then that would create this right here, the MgBr, and then 1, 2, 3, 4, 5, 6, like that. And then you wanted to do like, let's say 1, 2, 3, 4, 5, 6, that Br to get to that point, right? But this Grignard here, there's a problem. It won't do that. This carbon that is attached to the Mg is negatively charged. We have a carbonyl carbon that is electrophilic. So it will not attack this thing that we try to add onto it. It will do an intramolecular reaction instead. Right? So that's a problem. So what we have to do, which is the new thing in this chapter, is use a protecting group to protect this carbonyl here. Oh, right. So this is a new reaction we haven't learned yet, but I'm about to go over that reaction, right? I just went over this like thought process, like thought thing, to show like why we can't use Grignard automatically in this case.
So,
Uh-huh.
like this, if we, let's say, we formed a terminal alkyne
Mhm.
and then made it, or then we reacted with like, NaNH2 again, so that it would become or no, yeah, so it would be like an anion.
Yeah, an anion.
That would also.
It would as well. If there was a carbonyl somewhere in the molecule. In the other examples, there was no carbonyl. You didn't have to worry about that.
Right.
But now in this new chapter, you're gonna have a carbonyl in your molecule where you do have to protect it. Right. Yeah, but that's good. That's good that you answered Grignard because I wanted to like make you guys realize like this Grignard here, usually it works, but now it doesn't work because of this carbonyl present here. That's good. Nice. So let's learn about that protecting group now. How we can protect the carbonyl, do the Grignard reaction we want, and then deprotect the carbonyl to get back to the aldehyde or ketone. Okay. So let's start with a carbonyl like this. The protecting group is going to convert that carbonyl into this group here. Have you guys seen that before? Does that look familiar? Yeah, looks like a face, kind of, or in a goat. Okay. So, actually, before we go over that, let's go over the terms acetal versus hemiacetal. Okay. An acetal is when a carbon is attached to two OR groups. A hemiacetal is when half of the carbon is an OR, the other half is an OH, alcohol, right? So acetal, carbon has two OR groups. Hemiacetal, half hemi, half OH, half OR, hemiacetal. Okay, so what is this here? What is this carbon? Is this an acetal or a hemiacetal? Acetal, right? Because this carbon here has an OR, OR. Both of them are OR, so this is an acetal. And since it's cyclic, it's specifically a cyclic acetal. Where now this cyclic acetal here is not electrophilic. It's not going to react with Grignard. It's safe from Grignards. Right. And the reagent to do that is this diol here in some kind of acid, like H2SO4 or H2O plus. Right. You could see it like this on the exam or practice sometimes. You could see it like HO, CH2, CH2, OH. That's the same thing as this HO, CH2, CH2, OH. Right. Okay. Now let's go over the mechanism of this here. Every single step here is reversible, right? We have this diol here. Is this a weak or strong nucleophile? A neutral alcohol?
So we,
Yeah, weak nucleophile. It is not strong enough to attack this electrophilic carbon and pop the double bond on the oxygen. You know how other strong nucleophiles like OR minus is able to attack that carbon and pop the double bond to oxygen?
it's because that's true.
Yeah, because that's a negative charge. Since it is neutral, it's weak. What we have to do is activate this carbonyl, make this into a stronger nucleophile electrophile for this weak nucleophile to attack. Right? So think of it like this. This right now is a weak electrophile. This is a weak nucleophile. They can't react with each other. If we wanted to react with each other, one of them has to be strong. We can make this into a strong electrophile by activating it. Yeah. Question?
So this process would activate it.
Yes. This will activate it. And how do you think it can activate it? Like, what do you think is gonna happen if you have a strong acid here?
It's gonna dissociate and the H is gonna go.
Yeah, it's gonna protonate the most basic atom we have, which is the carbonyl oxygen here. That's the activating step. Protonating the carbonyl oxygen. So strong acid, like a lot of these mechanism stuffs, right? Don't just memorize it. Like understand the reason behind each arrow, like why that's going there. Since we have a strong acid, we have to look for our most basic atom, which is the oxygen here, right? And then that will do something to this carbonyl. So once we protonate this carbonyl, we get this activated carbonyl. right? Now, because this oxygen has a positive charge, it's now more greedy to gain electrons. It's going to pull on that double bond more, making this carbon have more positive charge or less positive charge. If this oxygen is trying to steal its electrons more positive, right? And that's the activation step. Now, this carbon is electrophilic enough for the weak nucleophile to attack, right? So now let's bring in our weak nucleophile. Right. So when you get stuck on a mechanism problem, think back to the fundamentals, like the basics, like acid base and stuff like that, like which one's your nucleophile, which one's your electrophile, and then just try random things and hopefully like something clicks, and then you get through the mechanism like that. Sometimes you make stuff up, you get it right, but you get stuck just like try to think from the fundamentals, right? Now this weak nucleophile here is able to attack this strong electrophile and then pop this double bond onto that oxygen right there to neutralize it, right? Now that's gonna give us this right here, where that double bond OH is now gonna be a single bond OH, where this oxygen here is no longer positive, it's now neutral because we gave it a set of electrons. The atom oxygen here attacks that carbonyl carbon, so we have to make a new bond between that carbon and that oxygen right here, right? Where this oxygen here is that oxygen there that attacked that carbon. Right. Okay, and now this is where people mess up on. They just leave it like that. But we know that this oxygen here is also attached to this whole group, and there's H right there. So we have to include that as well, right? That CH2, OH, and that oxygen is also attached to that H right there. What charge would that oxygen have with 3 bonds? Positive charge, right? So remember to include that charge in mechanism as well. Don't leave that out, right? That's a common thing that people leave out. The positive charge and the groups here attached to that oxygen, right? Now, here are the 2 points that are going to be common for these future mechanisms you're going to learn. You're going to deprotonate the group you want to stay and protonate the group you want to, leave, right? So since we just added this group here, we want that group to stay. But because it has a positive charge, it's a good leaving group right now. How can we make this into a bad leaving group here if we want it to stay? So how can we make this neutral here? Like this positive charge oxygen, how can we make it neutral? Okay. Yeah, deprotonate it by taking out the hydrogen, and that bond between the oxygen and hydrogen gives it a set of electrons. And to do that, we could use the conjugate base that we formed at the beginning, the HSO4 minus, right? So that's the deprotonating the group we want to stay part, right? Once that happens, we now have this neutral oxygen here, which is good because it's now a bad leaving group and we want it to stay. That's good. If we want this alcohol to leave right here, we have to make it into a good leaving group. How can we convert this bad leaving group into a good leaving group here? Protonate it, right? So we could use H2SO4, the acid catalyst that we reformed, to protonate that oxygen, to convert it into this good leaving group here, the oxonium ion. There, okay. I think I need more space. Let's see. Yeah, this is a long mechanism, but the patterns is the same. A lot of acid-base reactions, deprotonate the group that you want to stay to make it into a bad leaving group, protonate the group you want to leave to make it into a good leaving group. Right? A lot of acid-base stuff here. And the future reactions, right, in these chapters follows these same 2 points here. It's a lot of repetition. It's like the exact same pattern. right? It's just different groups, different nucleophiles. Okay, let me redraw this down here. Ooh, here. Okay, now once we have this good leaving group, we have to drive that good leaving group off by forming a carbonyl between that carbon and oxygen, and then kicking that water out. Right, so water will leave as a side product. Right. Okay. What is missing in the structure? What am I missing? Charge. Like what kind of charge? On what atom? On the O, right? Because the O has 3 bonds, so we have to include that positive charge there. That's important. And what does that mean? If that oxygen is positive, like what does that mean about its electrophilicity power? Strong electrophile, right? We know this is a strong electrophile. Do you know any nucleophile that can attack that strong electrophile nearby? The OH here, right? And if the nucleophile we see is on the same molecule as the electrophile, what kind of reaction is this called? Intermolecular, right? And in intermolecular reactions, what structure do we always form in all intermolecular reactions? Rings, cyclic rings, right? Cyclic structures. So that's how we get that cyclic acetal. That nucleophile attacks that electrophile, pops that double bond onto the oxygen right there. Right? And we will get this as a result. Right? And there's just one last step here to get to the cyclic acetal. Neutralize by deprotonating. And then, yes, H2SO4 acid catalyst. The H2SO4 gets reformed. Right. So now that is a protected carbonyl, a cyclic acetal that we formed. He could ask the reverse mechanism, like how to go from the cyclic acetal all the way back to the carbonyl. Right. Let's go over that too. But it's the same exact 2 points as we talked about, like deprotonate the group you want to stay, protonate the group you want to leave. It's the exact same thing. And I'll show you guys that now. Right. Okay.
So now we're gonna
Yeah, we're just gonna go reverse now. Right, but this time I'm gonna go a little bit quicker, but it will make more sense as I go through this. Right, it's the same like pattern, but like going backwards now. Right, because if he asks you to draw the mechanism from this cyclic acetal to this carbonyl, and he gives you water and H2SO4, right? This water here, right, came from this water that left in the original mechanism there. And in this water, oxygen is going to be that oxygen of the carbonyl, right? Okay, so let me walk you guys through this. Strong acid, what would that do here? Protein is one of the oxygens of the cyclic acetal. And notice how we're going backwards here? Because before we had that protonated thing here. This is going backwards now, right? Okay. Now, notice how we created a good leaving group, which is that group right there. We could drive that good leaving group off by forming a carbonyl, carbon double bond oxygen between the other carbon, between the, like this oxygen here and that carbon there. We could remake that double bond and then kick out that leaving group there, right? Like that. That's gonna go backwards even further, like this. But now that's neutral. This is positive charge. Okay, we still have an activated carbonyl. The water that we had in the reagent is going to be the nucleophile that attacks that electrophile there and pop that double bond to oxygen there. Right. And that gives us this. Uh-huh.
Since it's then technically that way anytime, so because there's
Ah.
put like more, like a
Uh-huh.
high ratio of like water
Mhm.
with,
Right. Let's talk about the Le Chatelier's principle. If you want more of the cyclic acetal, then H2SO4 is going to be like the same for both reactions because that's always there. More of this diol here
oh,
over the water.
oh,
If you want the cyclic acetal, you want more of the diol. If you want more of the carbonyl, more of the water. Right. The acid is always there for both. Okay. Now this here, what do you guys think we got to do next? What group do you want to keep and what group do you want to kick out? Right, this looks like a good leaving group, right? But do we want to kick that out? If we kick that out by doing that and that, that's gonna go back to this form here, right? We want this hydronium ion to stay because we want to go back towards the carbonyl form, right? And if we want it to stay, how can we convert this into a bad leaving group? Because right now it's a good leaving group. Deproteinate it. Nice, nice. So we could use HSO4 minus to deproteinate it, make it into a bad leaving group, which is good because we want it to stay. Nice. Which group do you want to kick out? And how can we turn this bad leaving group into a good leaving group? Nice. Proteinate it. Proteinate that group that we want to leave. Yeah. Yeah. See this common pattern? Like it's just like deprotonating the group you want to stay to make it into a bad leaving group and protonating it to make it a positive charge into a good leaving group. Right. This is going to follow like the future reactions. It's going to follow the same concept. Right. So don't get overwhelmed by like the amount of reactions that you're about to see. It all follows this similar concept here. It's just different nucleophiles, like an amine or an alcohol. It's the same mechanism, just different nucleophiles and electrophiles. And then once we have that good leaving group, we drive that good leaving group off by reforming that carbonyl and kicking that out. And that gets to this point. And this diol here. That. And the last step, neutralize that by deprotonating it and reforming the acid catalyst. So that was a reversible reaction there. This was the reverse mechanism, coming from a cyclic acetal back to the carbonyl, right? So this is the deprotecting reagent here, acid and water. Like you could use H3O plus as well. Okay. So now try this synthesis problem based on what we just learned. Um, yeah, I'll put that. Yeah, I think we'll have time to finish the chapter 17 reactions tomorrow, but not the nomenclature and the spectroscopy, HNMR, mass spec stuff. Yeah, we'll leave that for the final review like last week. Okay. What did you guys try doing first? Protect the carbonyl, and we need also acid, like H3O plus, let's say. It could be H2SO four as well. That would convert that carbonyl into the cyclic acetal, right? Okay. What is next? Yeah. Yeah, now we could turn it into a Grignard reagent. We could do Mg to insert that magnesium between that carbon and bromine, making this carbon attached to the Mg, the nucleophile, right? Now, what kind of electrophile do we want to add onto this Grignard to get this new group here, the CH2OH? This is probably the tricky one here, the electrophile, right? Yeah, aldehyde, right. Yeah, acid workup to get the O minus into the OH, right? And do you know what kind of specific aldehyde we want? With like, yeah, an aldehyde that has two hydrogens, so formaldehyde, right? Nice. Because you could say that this is our nucleophile here, which is that starred atom, and this is the electrophile here, the atom that the nucleophile attacks. This is the new bond between the star and dot atom, right? But we see that this electrophile here has an OH, right? And back in 118A, when we did Grignard reactions, whenever you see a new carbon group with an OH, it always came from a carbonyl, right? Where the electrophile was this carbonyl carbon right there. And that carbonyl carbon has two hydrogens, which are these two invisible hydrogens right there. If this aldehyde had an ethyl group, then there would be an ethyl group right there, but we had no R group there, right? Nice. And then acid breakup. Star dot, right? The star attack the dot, pop the double bond onto the oxygen. Oxygen minus gets protonated by acid workup. Oh, and this is an carbonyl, cyclic acetal. And then the last step here, to deprotect it, we need acid, H2O plus, water, and I see we also need heat as well. Heat to add enough energy to get to that point. Heat. The deprotecting step. We couldn't do Mg right away because that would make this nucleophilic carbon do an intramolecular reaction, attack that electrophilic carbon or carbon instead, but we don't want that. We wanted that carbonyl to be untouched. So we had to protect it first, and then do the Grignard reaction we want, and then deprotect it at the very end.
So, it's not similar to this condition, but kind of like that same concept, you would add on and then leave it on after.
Yeah, to avoid that spot being reacted. Yeah. And this is, yeah, protecting group stuff. Yeah. Okay. Now there is another protecting group for carbonyls, but you don't need to know the mechanism for this. Let's say we have this carbonyl here, and you see this kind of reagent, HS, and then CH2, SH, and then zinc chloride. It's gonna give a similar protecting group, but instead of oxygen, it's gonna be sulfur, right? And then to go back to deprotect that, it's weird. It's like a chemical soup, like mercury, Cl2, Ca, Cl3, CH3, Cn, H2O. Don't worry about the mechanism. I don't think it's gonna be like covered. Right. So you could use this protecting group as well. If you use a reducing agent like H2PDC, you could reduce that thioacetal. This is called a thioacetal into an alkane like that, where the two hydrogens here comes from these two hydrogens here, from the H2 PDC. Okay. Okay. Now, there are some synthesis that requires you to use both protecting groups, because you notice how there's different deprotecting reagents for each protecting group. If you had multiple carbonyls, you could protect one carbonyl first, and then the other carbonyl with the other version, and then deprotect it using the different deprotecting reagents. So let's look at this example here. Let's say we have this, and we try to create this here. Let's see. Yeah. Okay. Yeah. Try the synthesis from here. Yeah. Uh-huh. Yeah.
I didn't know anything. Oh no. I spent like a long time studying Deal's orders and before it's only one question.
Oh no. I heard like the reactions, there was just like one for each, because there was like so much reactions to cover.
And I spent so long studying
All kinds of those.
benzene.
Benzenes, yeah.
Only like four of the exam was all.
Yeah.
On the last exam, we had like 8 or
8 or 9. Oh my God. Was it mostly like vocab?
Yeah, I want-
Oh no.
yeah, I would say the website was a little bit-
Yeah. And the mechanism was 16 points, like I heard.
Yeah.
Oh, yeah, the,
Three vocables.
the synthesis was 12. for
12
both
points.
sides.
Oh my God. So it's mostly mechanism and synthesis.
I messed up the mechanism because I didn't know what toluene was.
Oh, toluene,
I
yeah.
didn't know what toluene was.
Did you guess? Or did you just put an empty
Benzene.
benzene? Partial credit. But did you get the rest of the mechanism right? Like with
I
the
knew about it. I just didn't know what
Halloween was oh, now, what did you guys try doing first here? What did you guys notice about the differences between the reactant molecule and the product molecule? Oh, what did you guys try for the synthesis problem? Yeah. Ozonolysis first, right? Because we had a ring with an alkene, and then now we have a linear chain. And to break it open, we know that reaction that cuts up bonds, ozonolysis. Nice, nice. First, ozonolysis. Okay. Let me see. I'm gonna redraw this really quick. Six, seven, 2, 3, 4, 5, 6, 7, and then aldehyde right here. Okay, let me get rid of this. Okay. What reaction do you guys know that will convert an aldehyde to an alcohol? Are we oxidizing or reducing? Reducing, right? And what reducing agent do you guys know? Oh, MCPBA is an oxidizing agent, right? Which oxidizes NH2 to NO2 in benzenes, or it can make epoxides from alkenes. What two reducing agents back in 1A have you guys learned? Lithium aluminum hydride, LiAlH4, or NaBH4, right? But there's a problem here. We can't do that because what would that also reduce? The ketone, right? The methyl ketone. So we have to protect it. But we can't just use one protecting group because what did we say was a better electrophile? Ketone or an aldehyde? Aldehyde. So let's say we use the thiol protecting group first, right? With H3O plus, it's gonna go for the more electrophilic functional group, which is the aldehyde. Right? And now from here, we could protect that ketone carbonyl using the other protecting group, the diol. Right? Now from here, we could deprotect that aldehyde using the weird chemical soup. Which will not deprotect the diol. This thing here will not deprotect the diol. Right? That will convert that back into the aldehyde. Now from this open aldehyde, we could reduce it without worrying about reducing the ketone because the ketone is protected. H. And then the last step, H plus H2O heat to deprotect the diol back into the carbonyl. So we had to use two of the protecting groups here. The first protecting group protected the more electrophilic aldehyde first. And then we didn't want to reduce this, so that's why we didn't do LiOH4 first, because we wanted to keep that carbonyl there. We didn't want an alcohol here. So we protected that carbonyl with the other protecting group, the diol. And then we use this deprotecting group, which will only deprotect the thiol acetal back into the carbonyl. And then we reduce this aldehyde to the alcohol we want, right? Which will not react with this acetal here. Once we get the alcohol we want, we get back our ketone by deprotecting that this acetal here using acid, water, and heat. Okay.
When we referred from that bioacetal to ketone or
Carbonyl.
or carbonyl, will we have to write out the HgCO2, calcium carbonate, CH3CN, and H2O, like all of that? Like the entire wall of text, like underneath everything.
Yes. Yeah, unfortunately. Yeah. Well, for the series, we had to, and Pascal most likely you have to as well. Okay. Now let's look at some reactions of aldehyde and ketone. Oh my gosh. Okay. So there's reduction, which we just did. But let's say we have another functional group like an alkene in the molecule. Will a reducing agent react with an alkene? Like let's say we put lithium aluminum hydride, LiAlH4. You could use NaBH4 as well. Will the alkene be touched by the reducing agent or no? Oh, I think you're thinking about H2PDC. H2PDC would react with this alkene, but LiAlH4 or NaBH4 would not react with this alkene here. So the alkene will stay untouched and convert that aldehyde into an alcohol, reduce the aldehyde into the alcohol. Right. We could also do organometallic reactions like Grignard or organolithium. Like let's say we have this structure. And we have this Grignard reagent here. Yeah. Okay. This Grignard here, we know that carbon is nucleophilic, partially negative. The carbonyl carbon of this aldehyde is electrophilic, partially positive. The alkene here, you can think of that as a nucleophile because when we were in the alkene chapter, it did serve as a nucleophile which attacks like an HX, X2, or some other reagent, right? Nucleophiles do not want to react with nucleophiles. So the alkene here would not interact with the Grignard. Is Grignard a strong or weak nucleophile? It would be strong nucleophile, right? Organic metallics, they give them as a strong nucleophile and a strong base. This weak, unactivated carbonyl here can get attacked by a strong nucleophile here. In the other example, when we did the diol, it wasn't strong enough to attack this weak electrophile. But this strong nucleophile here is strong enough to attack this weak electrophile. So we don't have to activate it here. It would just go straight for the attack and pop the double bond onto the oxygen here, which gets protonated by the acid workup, right? So we could say that this is the dot carbon. There's a new bond between the dot and star carbon. That star carbon has methyl, and the dot carbon is now attached to an OH, right? Originally, it had an O minus, but that O minus gets protonated in the acid workup step. Okay. Nice. And we already talked about how the carbonyl oxygen is basic, right? And that's how we could activate it using the strong acid. But now let's talk about the alpha hydrogen. The alpha hydrogen is acidic, right? So let's say we have this ketone here, and we have some kind of strong base, like N-butyllithium. Right? This carbon here is partially negative or fully negative because of that lithium there. Think of that as a strong base, right? It will act as a base rather than a nucleophile. Strong base over nucleophile. And bases, we know they want to attack hydrogens, grab hydrogens. The most acidic hydrogen in this molecule here is one of these alpha hydrogens here, right? This is the alpha carbon because it is one carbon away from the carbonyl carbon. This is not the alpha carbon. This carbon is the carbonyl carbon itself. The alpha carbon is one away, so it's either that or this here, right? The reason why that's the most acidic one is because when we deprotonate it, right? Let's say we give that carbon here a negative charge. Let's look at the conjugate base. What do you notice about this conjugate base here, where there's a negative charge on that alpha carbon? What can it do? It can do, yeah, so it can do resonance here, right? Because it is right next to the sp2 carbonyl carbon, right? And like you said earlier, like Grignard reaction, it's gonna be like a Grignard reaction, but you're gonna learn about that in chapter 18, right? That's chapter 18. This is gonna be a nucleophile here. That carbon can be a nucleophile as a Grignard, like a Grignard. It could be that, but it could also do resonance with the carbonyl here, right? And because of resonance, it's stabilized. That's why it's acidic. Right. Yeah. Right. So this alpha hydrogen is acidic because it gives a relatively stable conjugate base. If an acid gives a stable conjugate base, it is more acidic, and it's stable because of resonance. And later on in chapter 18, we'll learn that this negative charge on that carbon can be a nucleophile like a Grignard. This here is called an enolate ion. Because we learned that enols are an alkene next to an alcohol. This is an enolate, meaning that it's an ion, like a negative charge ion. Like it's a deprotonated enol. You can think of it like that, deprotonated enol with a negative charge, enolate. Yeah.
Another question about the previous reaction we did.
Yeah.
So we have the two steps. The first step being the MGBR, and then the second step is the deprotonation. So when you move the electrons up from the double bonded oxygen, you would get a carbocation there, and that's where you attach the MGBR from over there. but you said since it's partial negative, wouldn't you get, oh,
Right. There's no carbocation that's gonna get formed.
um,
This nucleophile here,
it touches right over.
yeah, it touches right away. And then this O minus here gets the H plus source.
Okay.
Yeah. Okay. Sometimes you might say it like this, like instead of kicking the double bond onto the oxygen, you know that the oxygen is gonna have a negative charge where you could just draw that arrow going straight for the proton source right away. So you don't have to draw this O minus charge there. But that's what you might say, like if you like do some like other reactions or like mechanisms notes or like you search up things online, you might see the arrow going from the double bond straight for the proton source instead of the oxygen here. Yeah. Okay. Yeah. Both of these are the enolate ions. Okay. Okay, so this is gonna be a preview for chapter 18. We have a negative charge on this carbon and a negative charge on the oxygen there. Which one do you guys think is going to be the nucleophile? Which one is going to attack an electrophile? This carbon or this oxygen?
That one.
This one? So this one is more stable, right?
Oh, right, because of negative charge.
The nitrogen is on one actually negative atom. Since it is more stable, it's less reactive.
Mhm.
This one is less stable, more reactive. So this is going to be the atom that's attacking here. Right, that's the nucleophile there. Right. That carbon there, because it is less stable, more reactive. Okay. Now a functional group that you guys are going to learn is a geminal diol. And what a geminal diol is if a carbon has two alcohols on it like that, right? On the same carbon. That's why it's geminal. You can see this as a hydrate as well. We could create a geminal diol from a carbonyl in two conditions, acidic conditions and basic conditions. Let's look at the acidic conditions first, right? Where if we want to create this geminal diol from this carbonyl, we could use water and some kind of acid, like let's say H2SO4. It could be H3O plus as well. Right. Okay. Now, what do you guys think is going to happen first here in this mechanism? Like think back to the fundamental basics, conceptual things. Look at the arrows, what's on it, and what's on the reactant. Right. And what kind of nucleophile and electrophile we have, like a weak one or a strong one. Yeah, this is our electrophile and this is our nucleophile. But notice that they're both weak, weak, and weak. We have to activate this to make this a strong one by protonating it using the strong acid we have. Right. So there's a lot of activating carbonyls in these chapters to make it into a strong electrophile. You don't need to activate it if you have a strong nucleophile already on the arrow, like a Grignard reagent or an OR minus. Yeah. Okay, that gets to OH plus. And now the weak nucleophile water can come in, attack that, pop that double bond onto the oxygen. OH. H plus. And then last step, deprotonate that OH 2 plus. to get to the geminal diol or hydrate there. Right, that is acid catalyzed geminal diol formation. We could also do this in basic conditions. Like, let's say we try to convert this carbonyl into this geminal diol using NaOH in water. Is NaOH a strong or weak nucleophile? An OH minus. So we don't have to activate the carbonyl. We don't have to protonate it. That strong nucleophile, we just go straight for the attack and pop the double bonds to the oxygen right away. Right. And that will give us this intermediate here, an O minus, OH. And the proton source here is not acid. It's not H2SO4 or H3O plus. The proton source is water. Right. When we protonate that O minus, we're going to kick out another base catalyst, OH minus. Right, because we're in basic conditions. We never have positive charges. We either have a neutral charge or a negative charge in basic conditions. In acidic conditions, we either have a neutral charge or positive charge in acidic conditions. Right. And that just gets straight to that geminal diol. Okay. I think that's a lot of information. I don't want to overwhelm you guys. But we could do like I think we could do some of these practice here, and I could walk around if you guys have questions, or we could like end it early there. Right. See, let's try these practice problems here. Oh, no, not the key. Yeah, I think we went over all of these reactions in this worksheet here today. Okay. This right here, think of it as R2BH. So this is hydrogen oxidation. And this whole thing here is a source of a carbocation on the cyclohexane here. Right. So this think of Pirukav's alkylation in this first step here, where the positive charge is that carbonate there. And we have a benzene ring here with a carbon group there. Right. See, yeah. In around 5 minutes, I'll go over these problems. Okay, walk around. Have you guys started like reading ahead for the chapter 17, 18 yet, or not yet? Let's see. But you guys are here though, like right after the midterm too. Like I expected like to be like empty. You're early, like I was like no one's gonna show up. Oh yeah.
Oh,
Oh yeah.
or you're graduating this quarter, right?
Yes.
You're not gonna do any more revision because you have to be a.
Yeah, I won't do like the content review sessions, but I will still do office hours for people to have questions and have to answer their questions. Okay.
Are you still gonna do training?
Tutoring, yes, I am, but not in person at Davis.
Yeah, just like there's.
Yeah,
What are your plans after you graduate?
I got into chiropractic school, so I'm starting that
Oh, cool. Wow.
July.
Wow.
Yeah. Yeah, thank you. And my sister's gonna be here. She's her first year. She's gonna start full time next year. So if any of you guys become like tutors, you guys can like my tutor or see her. I don't know.
Oh, that's cool. What is she coming from?
Pharmaceutical chemistry. So if you also go into pharmacy school,
Oh, wow.
yeah, so there's a lot of chemistry.
Yeah, so you guys must like chemistry. Oh gosh, it's time to like go on to yours.
Okay, so for the first one here, what is going to happen? Oxidize, right? Oxidizing agent, which this case we have Jones reagent. We have a secondary alcohol here, tertiary alcohol here, primary alcohol here. The secondary alcohol becomes methyl ketone in this case, yeah. If this R group here wasn't a methyl, then it's just a ketone, right? But in this case, this is a methyl ketone. Nice. Tertiary alcohol, no reaction, stays as an alcohol. Primary alcohol. So aldehyde would be if we used PCC, a weak oxidizing agent. Jones is a strong oxidizing agent, which oxidizes the primary alcohol all the way to carboxylic acid. Nice. Okay, that's the answer for that one. Okay, what would happen in this one here? Nice. Yeah, benzylic or allylic alcohols. And let's say this is 1, 2, 3. Which ones of these would get oxidized? 1, 2, 3. Yeah, 1 and 3. Because this one here is benzylic. This is the benzylic carbon because it's attached to the benzene. 3 is allylic because it's attached to an alkene that is not a benzene. This is not benzylic nor allylic, so nothing happens there.
Could you explain why benzylic and allylic carbons are more reactive?
Right, benzylic and allylic carbons are more reactive because
They're, yeah,
Did you realize that?
yeah, dehydrated, delocalized better. Like imagine there's a carbocation here, like when it leaves, if the positive charge here can delocalize with the benzene ring or delocalize with the alkene system.
Doesn't that mean like if it can delocalize more, doesn't that make it more like stable, making it less reactive?
Yeah, that's a good point. Let's see. Maybe it has to do in the case like it could exist more in nature, but that doesn't really like, because like in other cases, like if that exists more, then like sometimes that's the explanation. The other times there's other explanation. But for this explanation here, like there's more of that around for it to react. But in the other case, like where the negative charge is on the oxygen versus the negative charge on the carbon, the negative charge on the carbon is more reactive because it's less stable.
So you can just say it's like these houses more in excess.
Yeah, more in excess, right. But that's like good conceptual thinking though. Right, that oxidizes to a ketone. This one here stays as an alcohol. This allylic alcohol gets oxidized to a carbonyl, where that carbonyl is an aldehyde because of this hydrogen right there. Okay. What is the reaction of the third reaction here? Yeah, anti-Markovnikov. Yeah, right. Where in this terminal alkyne here, there is an anti-mark position, which is this position here. But there's no anti-mark or mark position in this internal alkyne here. So we're gonna get two different products, right? What will this terminal alkyne go into as a result at the very end? If we have a terminal alkyne reacting with hydroversion oxidation, what functional group do we always have? An eno that was always going to be tautomerized. But that eno that tautomerizes for terminal alkyne tautomerizes to an aldehyde. Always an aldehyde. Methyl ketone from a terminal alkyne. Yeah, nice. Let's say the aldehyde is that. Numbering it might help. 1, 2, 3, 4, 5, 6, 7, 7, 6, 5, methyl, and then 4, 3, 2, 1, 1, 2, 3, 4. But this internal alkyne here does not have a anti-mark position, So the carbonyl could be on carbon 2, like that, or it could go on carbon 3. Like this. 2 different products. Right. The terminal alkyne here always goes into the aldehyde. The internal alkyne here, the carbonyl could go on either carbon of the alkyne.
Did you just assume that this isn't?
Yeah, yeah. Just like ozonalysis or H2PDC, assume in excess, or MnO2. Yeah. Okay. The first reaction is last material. Right. Where we have a benzene ring. And what is this substituent here? EDG, EWG? Yeah. Oh, this is a little bit tricky because I think you're used to seeing it as a nitrile, right? But think of this, there's no atoms, it's just H and C's, R group. So R groups are EDGs, right? And we know EDGs are orthoparadirectors. Think of this as Friedel-Crafts alkylation, where the R plus source is this right here. Right. He didn't go over cyclohexanol BF3, but what that, yeah, I won't go over that. Yeah, but that's just a source of the cyclohexane with the positive charge there. Yeah. Para, because of steric hindrance. So this is what we get after the first step. Right. Now, the next 2 steps are together. They are one reaction. Think of that as R2BH, NBBN. Right. That is hydroversion oxidation on a terminal alkyne. And like we said in the last example, we always get an aldehyde. Oh, wait, no. Aldehyde. There we go. Okay. Now we have this aldehyde, and let's say we have this weird looking Greek nerd. We know the carbon attached to the magnesium is partially negative, and the carbonyl carbon is partially positive. So this Greek nerd attacks that carbonyl carbon, pops the double bond onto the oxygen, which that O minus is going to get protonated by the 5th step. But let me do this separately so then it makes more sense. Right. Pops that there to make O minus. Okay. And that would give us this intermediate. O minus. This is the dot. I'm going to leave this hydrogen invisible now. Make a new bond between the dot and the star. This star is attached to CH2. And then this this cyclic acetal. Okay. Now the 5th step, H3O plus, here we'll do 2 things. Right, H3O plus and water. What will it do? H3O plus, water. It's gonna do 2 things to this molecule. Yeah. Yeah, protonate the negative oxygen to become OH. And what else will it do? This is the thing we learned today. The new thing.
Oh, it's.
Deprotect that acetal into the carbonyl, right? So this carbon here is the carbonyl, which this carbon here still has a hydrogen. So that's the hydrogen right there, which is an aldehyde, right? Okay, now we're just bringing in the last step, PCC. PCC will is it an oxidizing agent or a reducing oxidizing agent, right? Secondary alcohol will turn into ketone. Final answer. Okay, nice. Let's see. We'll finish the reactions and mechanisms of chapter 17 tomorrow. And then hopefully we could do all of chapter 18 next week. And then the final week, week 10, final review on like everything for the final. Yeah. Let's see. There's a lot.